Yep, that's all set for you. Few more minutes. So today we have Dr. Akshay Balaji.
Not yet, doctor.
He's about to be a doctor. So Akshay is a second year medical student at the Hollywood Medical School. And one good thing about doing medicine is that you get experience in different hospitals. So he has worked in Hull as well as in Leeds and I think in York Hospital as well. And his research is more focused on cardiovascular surgery. And he has also recently working in the area of neurological diseases like neuroblastoma.
Glioblastoma.
And he's going to talk about his experience with medical technology, what is current status of surgical innovation in the current scenario, what can happen in near future. So I'll open the floor to you.
Thank you very much.
Thank you, and welcome to all the people who came online. So I hope you enjoy, and please ask the questions if you have any. Thank you.
Right, so thank you very much, Dr. Chauhan, and thank you very much for having me today. So just a bit about me. As he said, I'm a second year medical student at Holyoke Medical School, and my interests lie in cardiothoracic surgery. And recently I've been endeavoring in neurosurgery as well. And because I've met Dr. Chauhan, I've recently developed a passion for medical engineering as well. And current projects that I'm working on currently include some things I'm working on in neurovascular technology, such as intraoperative tumor detection and using segmentation to reconstruct 3D images. So without further ado, let's start. So I think before we can start on and look about what's going to be in the future, I think we have to do a bit of introspection and look back to the past. And the past, I think these were some of the most influential things that you'd see on a day-to-day basis in every surgical theater or every surgical unit. First things first is the X-rays. I think every single person has heard of this before, and it is probably the single most used technology in every hospital worldwide. And I don't know about some of the history about it is that it was actually discovered by accident while the person who invented it was working with vacuum tubes. And ultimately, he found out that he was able to actually project images onto a film, and that's how it was developed. And that's now how the basis for almost most of our diagnosing comes from X-rays and CTs. So it was one of the most influential things ever. The second thing I wanted to talk about is diathermy. This is a bit less known, but it's something that's found in every surgical theater. And what it is essentially using electromagnetic frequencies to basically burn tissue to stop it from bleeding. This is probably used in every theater worldwide for surgery because it's the quickest and efficient way to stop bleeding from fat or muscle. And the third one is a bit of a unique one in that it is the basis for all of cardiothoracic surgery that we do currently. And it was a machine that essentially serves as the heart and lungs when your heart is no longer beating in theater. The way we do operations in cardiac surgery is we try to stop the heart using a specific chemical called cardioplegia, and the rest has to be done while the rest of the body is getting blood. So this machine will take care of that. I'll go in a bit more detail, and I'll also ask your thoughts about what you think about this technology. And then the future of medicine, I think, can be robotics and artificial intelligence as the two biggest names in medicine and in all fields now are these two things. So I think we can get started with that. So I think we can start with the cardiopulmonary bypass. So it was invented in 1953, meaning that before that, we didn't really have much knowledge on the topic on cardiac surgery. Most of it was done open heart before that. And the problems with that was we had to cool patients down to around 18 degrees and basically stop circulation for a specific amount of time. The problem with that was we weren't able to warm them back up long enough or fast enough that they would die post-operatively quite quickly, suffer strokes, have numerous complications. But now we have this machine, which I'll explain how it works, is that it basically is powered by centrifugal force is the main mechanism how it pumps blood back into body, and it has an oxygenator which uses diffusion to basically oxygenate the blood that it gets back from the heart, and it goes in a cycle like that. So I wanted to put this to the floor, anyone online as well. What do you think the biggest problem during design of this was?
I guess testing is going to be an issue in an ethical way, as well as suitable testing for a range of patients.
Yeah, so that's one of the main issues, because in cardiac surgery we have a very vast range of patients, from people who are around 2 days old to patients in their 80s and 90s. So there's a lot of fluid dynamics that come into play, which I'm sure you guys understand more than I do, but we'll get into that as well. What more mechanical problems do you think they would have encountered in this situation? Yeah, so the blood clots, that's one of the main issues with any sort of machine, is that blood, once it is in its natural state, will try to clump together to form clots. And that's something which was a big issue when they started developing this, because they couldn't think of ways to thin the blood. And that's where drugs that we currently give in theatre are very useful. So this is what we give heparin, because once your patient is heparinized, the blood becomes more viscous, and it becomes very thin, becomes more thin, and there's less platelet circulating at that specific point in time. So that's one of the most important things. So these are some of the challenges that I've spoken to a lot of perfusionists who work with this machine, and these were some of the things that they thought were the biggest challenges when it came out. The first thing being maintaining a laminar flow. With cardiac surgery, and I'd say any blood-related field, if the blood flow isn't laminar and is turbulent, you will have ballooning of vessels, and the vessels will actually shear in on themselves. So you will basically get what's called an aneurysm or a rupture. And as you can imagine, that's a lot of blood in a very small space, which can be catastrophic. Yes.
This machine like this, is it connected into multiple points, or is it just one in, one out?
So it is one in, one out. So the heart's anatomy, we have what's called the right atrium, which is where all the blood's coming back to the heart. And you put one pipe into that, and then you put another pipe into the aorta, which is the big vessel, which carries oxygenated blood to the rest of the body. So it's one pipe in, one pipe out. So this one pipe going into the heart, which is the one that's giving all the oxygenated blood back, is using centrifugal force, whereas the other one is basically suctioning all the blood out of the right atrium, if that makes sense. So one's a vacuum and one's pumping actively. And the problems with that is, once you realize that you need to put heparin, which is to thin the blood, you will actually get a very more fluid flow. And that's one thing why we have to make sure the patient's adequately heparinized throughout the procedure. The second thing is, when patients are not having heart function, you need the pump to be very resistant to many different things, including electric shocks, because sometimes we have to defibrillate the heart to restart it while they're still on bypass. There's loads of different things that come into that, but from my understanding, there's a lot of issues that can go wrong with that. And the other thing is pressure control. When you're operating on the heart, pressure of the blood has to be very, very tightly regulated, because anything too high could cause damage while you're operating on the lower part of the heart. So this is where I believe you need to consider Bernoulli's principle and something in medicine we call Reynolds number, which is about how you calculate the viscosity of blood. So if we break it down into the simplest problems, I think it's, can blood move forward? What's going to be pushing that blood forward? And what are the problems we're going to face? If you break it down to those 3 steps, you get these challenges and the solutions that come with it, which were heparin, which were, I think with the pumps, they made them more durable and lightweight, so that they're able to spin for much faster and much longer. And the pressure control, this is where you have to consider the physiology along with the mechanics as well, because the human body plays by its own rules. So the next one I wanted to talk about was the diathermy. So I mentioned that it's basically electrosurgery, and it uses high frequency electromagnetic waves Do you guys have any thoughts on how you think it works? That's all right. Just take a guess. How do you think it's generating that heat? So the word diathermy comes from the Greek word heat, meaning both, and heat.
这个人应该是个大佬。
Sorry, someone's speaking. I cannot hear anything. Sorry, could you repeat that?
Or if there is any question, you can put it on the chat. I'll have a look. You can continue.
Yeah, so
Keep an eye.
as you said, it's basically just electricity going through one side and it's coming out the other, and it's causing an exothermic reaction, which is what's causing the blood to coagulate faster. But the reason why this is quite intelligent is that high frequency is actually causing the blood itself to start to coagulate. So it's activating proteins within your own blood to actually form a clot as well. So it's not only the physical side, it's also the biochemical side of biochemical reactions. So what material properties do you think you'd have to prioritize when you're designing this? Because obviously it has to be able to deliver quite a high electrical charge.
These are conductive.
Yeah, needs to be very conductive
Non-reactive.
and reactive. And how big do you think something like this would be? Yeah, so it's actually a handheld device, which is almost the size of a pen. So it's quite a small thing, and that's why it needs to have a very large power source externally connected to it. And that is a very important part of surgery, because without it, you'd have lots of problems with bleeding. And the old adage is, put pressure on it, it will stop. That will work until it doesn't. Let's see. It's not working. Right, so this is my general schematic for how I approach medical technology is identify the problem, and then the first thing I would suggest is look at the physiology behind whatever problem you're trying to address. Because in medicine and in engineering, they're quite very different in how you'd approach a problem. In medicine, we try to think, what's the body's natural response? And in engineering, you try to think, what can I do to fix it? And those are the two diametrically opposed things. So I think a combination of the two will help you create a better solution. And we'll come on to some drawbacks of the current demographic and the current state of medicine as well. So thinking of a mechanical solution, which is your area of expertise, and thinking of the physiology, where they meet is where you get your amazing solution. And then think about the barriers to implementation. Does that make sense? So present day practice. Every theatre is different, and also everything, it depends on money, but there's some things that won't ever change. We are currently moving to a scape where we're trying to get more minimally invasive. So as you can imagine, cutting a big hole into someone has a lot of problems that go along with it. One of the main ones being infection. So the ways robotics have come into play is that robotics allow us to make a smaller incision and work deeper in the cavities of the body with many different probes and also many different cameras, etc. But again, like I said, there's always some problems that can be improved on and fixed. So just for you guys, some of the physics behind it is kinematics. The way the robot looks is it has numerous arms but at different joints that are work. But as you can imagine, it's quite large, and you're trying to operate on something the size of your fist. It's quite a large thing to try and get near a small cavity. And this is where there's a lot of potential improvements. But before I get on to that, I was going to ask, what do you guys think about this design? What do you think could be changed?
Face looks very bulky, quite some scale,
Mhm.
but like the actual end effector looks huge.
Yes, it is quite large. So each of the arms can actually have smaller instruments attached to them, but these arms actually tend to have to be manually moved to the position of the operating field first. And then they can be moved within it with a surgeon sitting in the corner with a console, which basically acts, it sort of looks like a video game, but it has a lot more degree of rotation and everything like that. Do you see any other major problems that go along with it?
I don't know, it's shown that it's rotational movement.
Yes. Yeah, so that was what I was getting at with this image, is because I didn't want to show it to you. The rotation on these are actually very, very good. However, what's quite difficult is that because of its size, the rotation isn't limited to the actual instrument. It's the actual robot itself that's limited. So movement-wise, it's not able to move laterally, whereas you can rotate it within the cavity all you need because it has 720-degree rotation. So that is actually one of the big issues we have with it. The other issue is with the camera that comes along with it. So these cameras are actually very high quality, but that's not the main issue. The issue is actually with depth perception. With these kinds of things is you can never really get a 3D image. You always will see a 2D image of it, but it's quite hard to see the 3D. So I was going to ask, what do you guys think is a way we could augment that? And the key is in what I've just phrased it.
Yeah, start looking at potentially virtual reality or AI goggles.
Yeah.
Trying to get a second camera on there, so you've got 2 points of view.
Yeah, so that is one of the new emerging technologies, because it is some way to basically 3D something that's 2D, so you can make something that is more conceptually easy to see. Because as surgeons, we try to look at something in its three-dimensional space, whereas if we can only see like a frame of it, it's quite hard to figure out where bleeding is coming from and that kind of thing. And also it's quite an obscure, small point of access. So that's another issue that comes with it. I was gonna ask, what are the trade-offs between adding more degrees of freedom to the robotic arm and maintaining structural stability? Cost is one of the biggest ones.
Complexity.
Yeah. So could you elaborate on what you think would be the most complex in this situation?
Well, the more degrees of freedom you have, the more you have to think about your kinematics. Because to get to points, there'll be the more points of freedom you have to get to the same point, there'll be infinitely more ways of it to be able to move to that position. So
Yeah.
you have to figure out which is the best way to move that way. Requires a lot more like control to be planned and stuff.
Yeah, that is very much true. So now this is the bulk of my lecture. Is I'm going to be discussing a bit more about what I think is the future, and I want some input from you guys about what you think are potential problems that we could solve in the near future. First one being, because I said I am a geek about the heart, first one is going to be artificial hearts. They have existed for around 1 or 2 decades, and the first one implanted in 2014, I believe. And that patient did survive for quite a while. I think it was around 4 years, but there is quite a lot of problems that go along with it. So I wanted to ask, what do you guys think the main issue with something long-term being? Yeah.
Rejection.
Bodily rejection is one thing that many people don't consider because it's about a mechanical thing, whereas your body will react to any foreign objects. So that is one of the very key main problems. Blood coagulation is another, because anything flowing through this has to maintain your blood's natural viscosity, and blood thinners over a long period of time with patients in this kind of situation who are basically in dire situation with low cardiac output and lots of different problems. They will tend to have very limited mobility because when their blood's thin, they also have decreased oxygen binding capacity, and issues go along with hypoxia. Any other issues? There's quite a few that go along with this one.
But then like material longevity would be a thing. So obviously the body can repair its own system.
Yeah.
If you put a polymer in there, there's no way to repair that. So it erodes or gets damaged, you just have to replace the whole thing.
Yeah, so erosion was one of the main issues with that as well, because they found that the actual metal that it was made of degraded quite rapidly, much faster than they anticipated. Why do you think that is? So you mentioned immune response because you were talking about rejection, and there's a lot of other reasons why it would degrade.
Sometimes I know that like different metals react with each other. So the iron in the blood might react with the metal or materials that it's made out.
Yeah, so that is true. Our blood doesn't just contain iron, it actually contains numerous other things as well. We have copper in our blood, zinc. We have a lot of different metals, potassium as well. We have different things in there that react quite a lot. And that's one of the other issues. The other thing is pressure. The heart itself I know everyone thinks about 140 over 90 or whatever that kind of number, but the actual output it's creating is quite jarring when you actually feel it for yourself. So metals have to be very resistant to that pressure, and that's a very big challenge to overcome. So that's why artificial hearts haven't taken over. But in the US, we currently use what's called an LVAD, which is called a left ventricular assist device. And these ones aren't replacing your entire heart, but they're just replacing the pumping chamber. And they're using a pump similar to the cardiopulmonary bypass, which is just using centrifugal force and just pumping the blood over. But you have to be on blood thinners. You're quite restricted because you cannot, blood is only basically funneled to your brain and to the rest of your organs, but it's not really going to your extremities. So you're very restricted in what you can and can't do. So there are some ideas on how to improve this. What do you think would be one? I'm going to try and feed this to you so you can get this very easily. So if the issue is that you're not getting much oxygen and blood to the rest of you, and you only have one central pump, what do you think you could do to change that? Put another pump in. And what are you worried about if you do that?
Synchronization.
Synchronization, that's what I was going after. Anything else? Non-laminar flow is the other, and along with that, competitive flow. So if they are in nearby vicinities, they could cause competitive flow to develop, and that's a big problem in itself because, again, you'll have prioritization of one stream of blood over the other, and that could lead to hypoxia or damage to one of the organs or neither. So some technology that is being developed by my brother is he is developing mini pumps to replace, instead of one big pump in your heart, you put mini pumps throughout the body. Once your heart pumps out of the big vessel, you have several key pumps, mini pumps in different parts of your body. So one in your arm, or one in each arm, one in each leg, one in the descending aorta, which is in your abdomen. So, and you'd have to figure out how you sync that. So obviously there's conventional ways, like you can think about Bluetooth and all that, but you also have to kind of think about what we do on day-to-day lives. If you're walking outside, magnetic interference, there's so radiation, there's so many different things that we face because these patients will get numerous x-rays, CTs, MRIs. There's loads of different considerations that you have to think about. And this is where the challenge lies, is you have to think about the medical application, but also the mechanical, because there's problems in both. And the second thing I wanted to talk about was nanorobotics. This is one that hasn't really been able to move forward as fast as they'd expect, but I assume you guys understand why that is. So I was hoping you could explain that to me.
Well, one of the big things is testing, like long-term testing, is they're very reactive. A lot of these materials that you use.
Yeah.
And we're not quite sure what they do once they're there.
Okay.
And because they're so small, they can go places you don't expect them to go. So they can somehow disappear from the bloodstream and end up in different parts of the body you didn't expect them to be in.
Yeah.
Another big thing is actually creating devices, long-term manufacturing.
Yeah.
A lot of the devices that I've heard about are extremely hard to manufacture and require a lot of skill.
Yeah.
And unless you have the nano capabilities of Intel, you're not going to be able to use them on mass.
How big do you think the scale would have to be? So from micrometers, nanometers, centimeters, how big do you think these would have to be able to be used in microsurgery, in heart surgery, for example?
We're talking about robotics or like just delivery of
Robotics. So one of the potential applications we've been discussing in the cardiac field is robots to clear plaque that develops in your blood vessels. So over time, once people pass the age of around 16, your body's just starting to build fat in the arteries, and that will eventually lead to cardiac events like heart attacks and things. And one of the potential applications of nanorobotics was that we'd be able to deploy these robots to basically clear those plaque off the walls of the arteries. So how big do you think this would have to be in terms of scale? Yeah, it's ridiculously small because the closer to end organs you go, the more small the vessels get, which is it's logical sense where the minute you get to tissue level perfusion, it shrinks dramatically to your capillaries. The sizes, I think, are like 10 micrometers. They're very, very small numbers. And this is where nanorobotics has a major design flaw, is that you have to be able to, one, control them at that size to be able to actually have the power to have them within their small size. Because power of these things is quite high compared to the size of them. So there's a lot of design flaws in the batteries and how they're actually designed. So this is where I wanted to ask, what do you guys think is the single biggest problem with these in terms of the battery capability? Because this is one of the biggest limitations in most of our clinical practice with moving forward is we don't have technology that lasts for a long time against the body.
Batteries, you're just gonna get natural wear, like you see it in like phones.
Exactly.
After a year, your phone battery's 30% of the capacity, like lost 30% of its capacity now. If you're having something in the human body potentially for 10 years, especially such a small battery as that, you're gonna lose a lot of its charge and capacity quite quickly.
So the other discussion is you'd have to remove them after doing whatever procedure. But the issue with this is we aren't sure about the scale of which they'd be able to work, because you need to understand the mechanisms of how the plaque develops and how we can remove the plaques without damaging the vessels themselves. So how it works is the immune cells basically eat the fat that's deposited in there, and they form a hard fibrous layer around the artery. So it's almost embedded into the wall. So it's a very hard way of trying to actually get that out. One way that's been discussed is about laser guided technology. But again, there's quite a lot of problems with getting that in the scale of nanorobotics.
But it also point that the signals you use to control that, especially if we're trying to do a wireless mode where the signal becomes the wavelength of the signal becomes larger than the device itself. So you create an antenna that can pick up the signals.
Yeah, that is definitely. And the next thing I want to talk about is bioprinting, because this is another big field that has potential to change thousands, if not millions of lives. So there's some procedures that we do on a day-to-day basis, like kidney transplants, liver transplants, and all of them rely on a fixed donor pool, which is the number of people who are alive right now who are in the system who are going to actually donate their kidneys or livers or after death, that kind of thing. And the issues with that come, one, we don't actually know the quality of these organs until we get them out of the donors. And a lot of the time we have to test them with blood tests, but you don't actually see the organ in its entirety. Other thing is the pool sample size is so small, and there's a lot of people who are waiting for transplants. But this is where I think the scope is quite small. People think about printing new organs, but the scope of it now is becoming printing cells. A common procedure that is done is for pancreatic cancer. It's called a Whipple. And what that is essentially removing the pancreas from the equation and connecting two ends of the stomach to the small intestine. And the pancreas has a loads of function, including insulin production and glucagon production. So that's regulating your blood sugar. So bioprinting has potential to basically print a layer of a scaffold and embed those beta cells, which are the ones that make insulin, to essentially do the function of the pancreas without the cancer in them. And that's the new scope of this. It's been done, or it's been trialed. However, there's not much success because, again, like you mentioned earlier, rejection, big issue. There's longevity issues with these organs. There's perfusion issues because if there are cells in them, they need blood. And how do you get blood onto these biofilms, bioprinters? It's quite difficult. Blood is almost the single hardest thing we've ever tried to recreate, and we never have been able to successfully recreate it. We have done trials with this because in cardiac surgery specifically, there are a lot of Jehovah's Witnesses who might need surgery and they reject blood products. And because of that, there's a lot of problems that go associated with it. And you need blood to transfuse them when they get low. So there is current studies about developing new blood, but the problem with that is no matter how you make it synthetically, it has to be able to get perfusion from somewhere. So you need to find a vessel in the body to supply it, if that makes sense. So it's not just the product, it's always what will the body do in relation to that. The next one I wanted to really talk about is flexible robotics, because this is where you could change the world in surgery right now. So as we discussed with this, it's completely inflexible. It does not move well. And flexible robotics probably has the largest scope to change in the next 5 years or so in this kind of technology. The body has loads of crevices, loads of entrance orifices, loads of curved turns, which this does not take into account for. It's literally trying to do it from a straight path. So yes, we can cut into it and try to get that straight path, but it would be much easier if we were actually able to move around things, move through things, because that would actually give us more three-dimensional view of what's actually going on. And flexible robotics, again, is quite challenging because, again, as we've been discussing, materials, hardest thing to actually procure to develop these things. Two is, how do you actually control the flexibility? How do you make sure that there is adequate range of motion? How do you maintain that connection? All of these problems come together, and that's when you actually get the solutions. So the main baseline for this kind of technology is endoscopies or colonoscopies. This kind of material has been done for, I think, around 60, 70 years, but we haven't evolved from camera up someone's bum or up down their mouth. There's not much scope beyond that right now because we aren't able to do anything with it with robots right now up those canals. The significant problem we see in A&E is bowel obstruction, where someone's bowel is just blocked because ate something wrong, body had an immune response, loads of different things. And robotics, the potential for this is to literally cleave the obstruction or wipe it out or get them to pass it quicker. And this is where it is possible. However, again, it's about, can you pass something through that long? Because the human digestive tract, I don't know, is quite long. It's significant. I think it's around, the small intestine alone is around 30 feet. So that would need to have an exorbitant amount of material to be withstanding it. And also something that's quite commonly neglected is sterility. Anything that has any residue on it will have a foreign impact to the body. And that will need to be taken into account when you design anything. So these are all the problems, but there's a lot of solutions that can be done in place. One of which is like Neuralink and smart implants, because these will actually help us screen our patients before they come in. So Neuralink is, I think they've done their first in-person trials about paralysis and seeing if they're actually capable of sending impulses down to their spine. And studies have shown they can. It's just beyond that point, they're not able to receive any impulses because of that transection of the spinal cord or degeneration of the spinal cord. And there's technology right now being developed where their impulsive nervous system is basically sending messages to a computer, which is interpreting that and going back to the body. So these kinds of things can actually help us understand the baseline of what's going on in the body, which then can translate to why doesn't flexible robotics work? Why can't we do this? Why can't we do that? Because the data is what we're lacking right now with all these kinds of things, with models. We don't have the data to make accurate representations of these models. And that's where I wanted to ask, what do you guys think from this speech I've given you? What do you guys think are lacking areas in either surgery, medicine in general, that we could target with new technologies?
But like you said, with a lot of this, it's like when it comes to the application of a lot of it, it is that testing.
Mm-hmm.
And it's that essentially it's accounting for a lot of edge cases.
Yeah.
So the human body does what it wants to do, and it does lots of different things, and it's
Mm-hmm.
been shown to do things that we don't. There's lots of it that we still don't fully get why it does. So to be able to design something that can work within that,
Mm-hmm.
react to those changes, requires a lot of modeling and thinking.
Yes.
And then again, the only way to test it properly is to put it in a human patient that is
Mm-hmm.
fraught with difficulties.
Yes.
So I think, yeah, it's coming up with ways of us being able to essentially collect information
Mm-hmm.
so that we could have more accurate models that we create. Like you said, like stuff like Neuralink, stuff like that, having that understanding of how these signals and stuff that work in the brain means that, oh, we can take that and then use that information and data to test new products
Exactly.
for having to put under a patient.
And that's where therein lies the problem is we don't have the data to understand what's going on. And that is the biggest thing. Now, I want you guys to think from a like basics of whatever you understand about human body. What do you think are the biggest problems we face in medicine in terms of patients? What do patients come in with a lot of the time? Besides like regular illness, what do you think they come in with? Broken bones? Cancers. That's one of the biggest fields in technology is because there's numerous ways you can approach how you're going to remove that cancer. So right now, with all cancers, our treatment is pretty much go in, cut it out, bring it out, bring it back. Problem with that, they'll just keep growing. They'll just keep coming back. So that's the main problem with them. The way robotics comes into play is, again, going back to nanorobotics, is we as clinicians, we think that those can be used as vectors to basically inject anti-cancer drugs directly into those cells based on surface markers and proteins that these cells have unique to them compared to normal cells. The way we currently do chemotherapy is it targets any rapidly proliferating cells. And that's why hair falls out, nails break, weight loss, all these kinds of things just do not work. So these small nanorobots, if they could inject it into these cells directly, they would essentially remove all those negative side effects and target those cells specifically. And if longevity is a problem that can be solved, the idea is they prevent recurrence of cancer and just keeping it at bay, keep suppressing the cancer. So this is where you guys can put me out of a job.
Sometime back, I had seen a localized prostate cancer, like, what do you say, a device which would be introduced to a needle.
Yeah.
It was a radioactive seed.
Yes.
And the idea was that they could actually introduce the radioactive seeds in a localized vicinity of a tumor. In this case, it was a prostate cancer.
Yeah.
And the idea was that that localized radiation, which is exposed to tumor, it will kill it.
Yeah.
I have not seen it like translating into a clinical practice. Maybe I think there are some limitations to that study.
Yeah, so it is currently used in widespread practice, not in this country because it costs too much money.
Okay.
It is done in the US more, and radiosurgery is common in the US. It is one of the best ways, minimally invasive, that we can do, where patients are not candidates for surgery. And that is there. I think that is one of the biggest things is most people assume we can go in surgery, but a lot of people aren't candidates for surgery. And percutaneous interventions, technology is where those patients can find success. So I think the biggest change for cancer would be technology and immunotherapy combining together. With that, you'd have to think of ways to have receptors on the nanorobots themselves so that they don't react with the body. And you'd also have to be able to recognize what the other cells are in them. So that's the biggest thing. But when you put bioprinting in that mix, that's where you have a potential solution. It's just about the execution of it. And I think that would be the biggest thing I can think of. And I think that's all my presentation is, but I'm happy to take questions.
Quick question about nanorobotics. In terms of propulsion for these robots.
Yeah.
Do they commonly just rely on being in the bloodstream, just going with the flow, and once it's where it needs to be, dealing with the problem where it needs to be?
So it's not been tried. That's the main issue.
Right.
We haven't actually tried it, but that is the working theory, is that it would just flow with the body. But again, you can understand the problem with that is it relies where the blood's going. So we don't have much control where blood's going beyond you put it in there, it's going to come back to the heart at some point. That's all we really can control about it. So if you're trying to target a specific tumor, let's say, you need to inject it directly into that bloodstream going to that tumor. So that is possible because the way we do surgery on tumors is we try to isolate its blood supply. So that is something we try with immunotherapy now. But with nanorobotics, the goal is essentially once it gets into that, it will actually have a more robust image because the vasculature of tumors of the brain itself is too complex for us to imagine. We actually don't have an idea of what the tumor's blood supply looks like. We've just about managed to map the brain now, but we haven't managed to map the tumor's actual blood supply. We can see the big structures, like there's 2 arteries going into it. We can see that, but we can't see the branches and branches that go into it. So if we were to inject those nanorobots into that big vessel, they could branch into the smaller ones and target it from all directions, if that makes sense.
Obviously, we don't know a lot about who you say the blood vascular system within the tumor itself.
Yeah.
Do we have an idea of the scale of that vascular, like in terms of the size? Would it be comparable to capillary?
Yeah, it would be very small because tumors, how they grow is there's two mechanisms for it. One is that it used to be a functioning cell that's been damaged, or second option is it never functioned and it just got worse over time. So those two ways that can happen. If it was a normal cell initially, there is ways where the blood supply might be resemblant to a normal cell. And that's one of the problems is we can't tell if that's a normal healthy cell. As surgeons, we can't tell if that's normal healthy or if that's cancer. Whereas the robot itself will be able to, from a microvascular point of view, would be able to tell that. That makes sense? Any other questions?
There's a question online.
My apologies.
What kind of sensors can you have on internal, like robotics?
What kind of sensors? So the ones we rudimentarily use are pressure, because the basic idea is smaller vessels, if it's getting the same amount of blood flow, will have higher pressure. So that's one. Temperature is another. But what I think is lacking is about specific antigens. So this is where biology and engineering has to come together. Is anything to do with bioengineering, you'd have to, with these kind of things, with sensors, I think you need to look at the cells themselves and look at how they're functioning in cancer versus healthy, so that you can understand what's different about them. And then those sensors would have to respond to the antigens themselves or the receptors on the cells.
And more about its actual environment.
Yeah.
The mechanics.
Exactly. So mechanical sensors will work to some extent of differentiation, but they will never be as good as histological. Like, because when we take like biopsies, for example, we're able to see on a very cellular level what's actually different. Whereas if you're looking in terms of blood pressure, temperature, there's variation within an individual and within the population. So you always will have to think, how am I going to calibrate that to each person, to each cell, essentially? Whereas if you look at the antigen, you'll actually know that's going to be specific to this cell. So it would have to be something like, so my perspective on nanorobotics is that it would have to be something coated with a biological material that can recognize these antigens. That's how I perceive it. But again, that might not be the case. Any other questions for me? Right. Thank you very much, everyone.
Really, thank you very much. Are there any questions online? Feel free to type it on the comments if you have any questions.
And if you guys could also fill in that feedback form for me, thank you very much.
Looks like there are no questions. So I would like to thank everyone online and everyone in the room who were present for this talk. And thank you for such a wonderful interactive session. And let's thank Mr. Akshay for
Thank you.
doing this. Thank you so much. Thank you. So close the meeting. Thank you.